We're talking about partial pressures. And I don't know, I think the quiz isn't so bad, and everything we've been talking about so far hasn't been so bad. So you know life has to start getting more complicated sooner or later. And here it is, right? It really makes a lot more sense, this whole idea of partial pressures. For example, you want to fill up your tire with air to, what is it, usually like 35 pounds per square inch, PSI or something, right? Well, that's not just one type of gas. It's all these gases together, right? I mean, you have, what's all in air? You have mostly nitrogen. It's like 70%. And then there's a lot of, anybody else know? Oxygen, about 20-some%. And then there's some carbon dioxide and some argon, and that's about it. But the point is you fill up that tire with 35 psi, just compressed air. It's not just oxygen, it's not just nitrogen, it's not just carbon, it's all of them put together. Their total pressure will be 35 psi, right? So what does the pressure do to the oxygen? What does the pressure do to the nitrogen? What does the pressure do to the carbon dioxide? That's what we're getting into. More like real life situations here, which really kind of makes more sense because you can't stop gases from mixing. It's impossible. Every gas is a mixture, except for the stuff we paid for upstairs. That GCMS I showed you, we need, to make that thing work, we need 99, they call it 5-9er, so that's why I got to use my fingers, 99.999% pure hydrogen gas for that thing to work. So that's, and then we run that through a filter. So that's pretty much pure, but everything else, it's a mixture. Okay, so let's take a look at this whole idea of partial pressures. Just how is pressure created in the first place? Had a little animation. What happened to it? It's gone. Huh. Let's see if I can find it again. There it is. I don't know. You see the little cover kind of bouncing up and down there, Gloriana? Right? This is supposed to be my little thing I found on the internet, stolen of course, about how gas pressure is created. What is it trying to indicate? How is pressure, gas pressure, created using this diagram?
Well, it's forcing that top to go up.
Yeah, how?
Pressure?
Yeah. But they're these little, so little spheres moving around are supposed to be the gas, what? The gas particles, molecules, whatever, right? And they're actually doing what to that lid?
They're going all crazy.
Yeah, they're going all crazy, just like a gas should, right? They're all not going to move in the same direction, random motion, but they're colliding with it, right? If I heated this up, that's what, you think with everything they've got going on with computers and the internet and things, that they'd have better things I could steal than this, Yesenia. I mean, there should be a little dial here that I can turn and crank up the temperature. And then you'd see, what would be the change? Everything would go faster. It hit the lid harder, the little lid is going to go up, right? So if you don't want the lid to go up, you're going to have to exert more pressure to keep it down, right? Okay. Brianna, right now, if I could have that actual physical apparatus sitting right here, right, sitting right here on the bench, and somehow right in here, this was sealed so that gas can't leak in or out, what would be keeping that lid down? Well, gravity's one thing. Good. I didn't even think of gravity. I was thinking of something else. What was I thinking of? Atmospheric pressure. But gravity's definitely a good one, right? Because the lid's got mass. But atmospheric pressure is really what's keeping it. Because remember, 15 pounds per square inch. 15 pounds. I mean, that lid, I'm sure, is a few pounds, but not near as much as atmospheric pressure. Okay. But gravity plays a role. Good. Okay. Partial pressure and total pressure. So, Gloria, let's see. We've got some hydrogen over here. I wish these little guys were moving around, but they're not. 0.6 moles of it, and it's 0.5 liters at 20 degrees Celsius. And then over here we've got 5 liters again at 20 degrees Celsius, but now there's supposed to be 1.5 moles, so there's more of them flying around. Okay, and one is hydrogen gas, and the other one is helium. Notice how the two little balls stuck together, so showing their molecules. The other one is helium, just monatomic gas versus diatomic gas. But the idea is under this box is if I combine one with the other, and then they want to know how many of these little weights would you have to put on top to keep that lid at the same height. What would you guess? What would you guess? All right. Here I've got 2 of those guys. Here I have 1, 2, 3, 4, 5, right? Yeah, it's probably 7, right? And that's how it works. I move my little box here. Yeah. 7. Right, to keep it at the same height. Okay. But we're not going to be talking about counting weights. We're just going to be messing with atmospheres, right? So if you had 2.9 atmospheres of one gas and 7.2 atmospheres of the other gas, you put them in the same container, well, then your total pressure, just add them up, 10.1 atmospheres, as long as you keep the volume and the temperature the same. Right? So you can just add up, because pressure doesn't know what gas is which. Pressures, they just add up, right? I mean, they just add up. And that's kind of what one of our equations is going to be saying. P total is the pressure due to one gas pressure. Now, if we only have 2 gases, we're only going to be adding up 2 pressures. So one was the pressure due to hydrogen, the pressure due to helium. But we're not supposed to say the pressure due to hydrogen, the pressure due to helium. We're supposed to say the what pressure of hydrogen? The partial. The partial, right? The total pressure is the sum of all the partial pressures. The partial pressure of hydrogen, the partial pressure of helium. Okay? So that's the terminology we're starting to get into. So that means a whole bunch of new equations here. And here's the one we just talked about. Right? The total pressure is the sum of the partial pressures. Okay? If you have 2 gases, A and B. Erica, what do you think this equation is trying to say? Erica, what do you think that equation is trying to say? NT equals NA plus NB. What was little n? N was moles. So probably the total moles equals... Yeah, they don't. That's why they're weird. Why don't they stick with partial moles? They don't. The total moles is the sum of the moles of gas A. You know, just add up all the moles of all the gases present, and you get the total moles. That kind of makes sense. Okay. But yeah, they don't use the word partial anymore, though. This one's kind of odd. I don't think we're going to use it much, but we better be prepared in case it's in the homework. So you recognize Na. Na is going to be the number of moles of gas. Which one? Gas. The subscript. A, right? Na is the number of moles of gas A. Nt is total moles. So if I divide the moles of gas A by the total moles, I get some fraction. Well, here's the symbol for it. XA. But what do they call it? I guess you could, Christian, say the fraction of gas, the fraction that are gas A molecules, but you're not supposed to. What are you supposed to say? It starts with an M. Mole fraction. XA is the mole fraction of gas A. If you had a little b down there, that'd be the mole fraction of gas if you had a little b down there, that would be the mole fraction of gas B. And you'd have to put a NB up on top. Right? So you just kind of follow the notation. So you're only going to be given one equation, but just realize, oh, if that's a B, well, then this has to be a B. Okay? So mole fraction of hydrogen would be the number of moles of hydrogen over the total moles of gas that are present. And if you add up all the mole fractions of everything, you get 1. Okay? So we'll be playing around with that. Now there's one other equation we're given. We're given PV equals nRT. But notice so this whole, all these equations, right? 1, 2, 3, 4, all those equations are at the top of the quiz. You're also given a fifth equation, PV equals nRT. But do you see what's missing? How do you get PA in the first place? Right? Because the rest of these aren't so bad. I mean, how do you get Na, the number of moles of gas A? Well, they got it. Either they tell you or they give you grams probably or something so you can convert it into moles. So all of these are pretty straightforward, right? Except how do you get PA and PB in the first place? There's no equation for it. So I'm going to expect you to make it. And it's not that bad. All you do is you use this. And that's why I'm not giving it to you, because there's so many ways to write them. You play with subscripts. We're going to make the equation. How do you get the partial pressure of gas A? Well, you just put a subscript on there. Put a subscript on everything. Okay. Except some things. So the partial pressure of gas A, we've got it. We got the equation. Except we put too many subscripts, Desiree, because some things don't make sense to put subscripts on. I'd say there's 3 things in there that don't make sense to put subscripts on. What's one of them? R, definitely. Get rid of the A on the R, because they just, right? That's up on the top of the quiz. You plug in the 0.0821 and quit. Yvette, what's something else? The what? Hang on. The N, though. N is the number of moles of gas A. And it's also up here a bunch of times. So the N, to get the partial pressure of gas A, you only plug in the moles of gas A. So this one don't mess with. Right? You see another one? T. Because well, it doesn't matter what the gas is, helium or hydrogen or what, they're all at the same temperature. So that one doesn't make sense. The other one, last one would be V, because they're all in the same volume. They're all in the same box. They're all in the same container. So if you want to get the partial pressure of gas A, just use PV equals nRT and plug in the number of moles of gas A. If you want to know the partial pressure of hydrogen, right? Solve for P. They have to tell you the volume of the container. Look up the gas constant. They have to tell you the temperature. Just plug in the number of moles of hydrogen if you want to know the partial pressure of hydrogen. Okay? So you just kind of put a little subscript on there. Right? That's the game that we're going to be playing a lot. Okay? So we're given a bunch of equations, 4 new equations, and then just realize how to play with partial pressures, how to get it. You put subscripts on the P and the N. Okay. We're almost ready to work some problems, except we're going to do this in lab. This is done a lot in chemical analyses because it's very simple and straightforward. And for example, now I just picked an equation because we've seen this stuff before, but instead of collecting, see, they're heating potassium chlorate in here. Right? They're heating it in there, and all the little bubbles are bubbling up through the tube, right? Coming up, and they're all ending up in here. So instead of collecting oxygen gas, you'd probably be collecting something much more expensive, right? Something that's a lot more worth collecting. But this would be pure oxygen, so if you wanted to collect pure oxygen, I guess. Okay. But the problem is So we're heating it up, and we collect this oxygen up there, right? And the more I heat it up, the more I'm going to collect. And this little level right here is going to go where? It's going to go, if I collect more and more oxygen, it's going to go down, right? Because it's bubbling, bubbling, bubbling. It's going to force out more and more and more, right? So it's just going to keep going down, down, down. So you don't want to go too far, right? But pretty much they want to stop right here. Can you see it? They want to stop right there. That's where they want to stop collecting. And the reason why they want to stop collecting right there, not above and not below, is if you stop collecting right here, what's the pressure on the top of this liquid? It's atmospheric pressure. If you go into a lab, how do you know what atmospheric pressure is? You have to look at this thing on the wall. It starts with a B. Does anyone know? It's got these tubes, 2 tubes of mercury in it. A barometer, right? And we'll do it. Someone in the lab is going to be forced to go read this thing, and then they're gonna see, okay, there's so many. It actually is. It's millimeters of mercury. There's a tube of mercury in there, and you read it. Okay, it's 700 and in this case, what? 756. It's 756 millimeters of mercury. So they write it on the board so everybody knows what atmospheric pressure is. So if everyone stops collecting right here, we know what the pressure is inside that tube. It's 756 millimeters of mercury. Okay? So that's how they know this. And they know this because they know the volume of that darn test tube or whatever the heck that is they used. So they know those two things. Stick a thermometer, right? Just read the thermometer of the temperature of the room. So you know this. Okay. So they know the volume of oxygen gas they collected, the temperature and the pressure. And they want to know how many grams of this KClO3 was there that reacted in the first place. Okay. So, does anyone see how to solve this before I tell you? They give you, whenever they give you volume, pressure, temperature, you know you're going to have to use PV equals nRT. Okay? So we're going to have to use PV equals nRT. We're going to have to use it. Now, to me, a big hint, just because I'm so used to skimming problems and, okay, how do you start? Well, when they give you all that stuff, you know you're going to have to use PV equals nRT. When they give you a reaction, now you have mole bridges, right? So if we know the moles of oxygen, we can get the moles of potassium chlorate. And if you know moles of potassium chlorate, you can use molar mass to get it. So we're going to use PV equals nRT. We're going to get the moles of oxygen, right? And then we'll use the mole bridge, right, to get the moles of KClO3. And then I guess finish the story, molar mass, and we'll get the grams of KClO3, and we're done. That's the big game plan. Okay? So if that's not complicating enough, none of that is the complication I'm worried about. All right? But first, just make sure you see the big game plan. Everyone see the big picture? Right? We're going to collect a known volume of gas over water, so we know what V is. Right? We know R, we know T, right? We know P. Okay, and we'll solve for little n. Make sense? And then use mole bridge to get moles of KClO3, convert them to grams. That's the problem. This is the complication. Just write this. Wrong. Because you want to use what for P? Yeah, we got to use ATMs. But we want to convert what number into ATMs? 756. And that's what I'm saying is wrong. Yeah, we'll get into ATMs, but it's wrong. That pressure isn't pure oxygen. Right? Because if you're going to use this equation to get the number of moles of oxygen, then you have to be using the partial pressure of oxygen. We're not using the partial pressure of oxygen. We're using the total pressure. What else is there besides oxygen in this tube? What other gas? It's O2 and no CO2. Because when they started, they're going to fill this tube all the way up to the top. Water vapor. And the reason why I know water vapor is there, because I know water evaporates. I know if you have liquid water, you definitely have water vapor. You can't stop it, right? You can't stop it. So what we are really using is total pressure if we use 756, because here I am, water. So the only trick to this is to take this 756, right, and subtract out the pressure due to the water. And how do you get the pressure due to the water? It's these tables. Right? So to use the right pressure, or the correct pressure, first, before you do anything, you take your 756 and subtract, right, the from the table the millimeters of mercury due to water pressure. Water's vapor pressure. Right? And you get it from the table. Yeah, right? You just look it up. Now I just made up this question before this morning, and I should have picked 30 because 32 isn't in the table. You see that? Right? Because I said the temperature is 32, and is there a 32 in the table? No. See that? So you would have subtracted out. I'm going to change it to 30. So then you can subtract out 31.8. Okay? So we'll have to change this to 30. Okay, so we'll subtract out 31.8. So before you even start this whole question of what's written in red, you have to get the right pressure. This has to be the partial pressure of oxygen, so you get the number of moles of oxygen, right? This has to be the pressure due only to oxygen, so you get the number of moles of oxygen. Otherwise, you're using the total pressure, and you're going to get total moles. It won't be right. So you have to do the pressure due solely to oxygen. To get that, take the total pressure, the 756, and subtract out the pressure due to water. And you don't memorize these pressures due to water. I have to give you the table. Okay? So that's the big game plan. Let's see if we can remember that when we get to it. Let's see if we can work out some of these. Lauren, we want to calculate the total pressure in atmospheres of a mixture of 0.02 moles of helium, 0.01 moles of hydrogen, in a 5-liter flask at 10 degrees Celsius. So out of all those equations we have to work with, right? Here they are. What would you use? I hear first one. I like what Christian's thinking, the first one, because he sees PT, right? Because they're asking after total pressure. But if you use this one, you have to know the partial pressure of hydrogen, the partial pressure of the other gas. So it's uglier. It'll be easier to use this one and just use what subscript? See what I'm going on? T. All right? Because if you do that, man, this problem isn't so bad at all. Do you see that See what happens then? If you use PV equals nRT and just use subscripts. Because what's going to be NT then? Jacqueline, what would be NT? Yeah, it'd be the 0.02 plus the 0.01. Okay, so then you get your NT, and you can solve for PT. Just make sure, the only other problem with this problem is to convert 10 degrees Celsius. Make sure that's in Kelvin, right? So did you see the trick to that? This one is the only other equation that we have to work with. This one would be, it would work, but it's going to be a lot of work, right? Because you're going to have to find the partial pressure of helium, find the partial pressure of hydrogen. It'll work, but it'll be a major job. This way would be a lot easier. Okay? Let's see if we can set up the next one. So I'm just trying to set them up because I want to get to that really hard question with collecting a gas over water. What volume of carbon dioxide gas at 21 degrees Celsius and 781 millimeters of mercury could be absorbed by 327 grams of lithium hydroxide? Stephanie, where is this question even coming from? Right? Does anyone have a game plan? Now remember that your guide, when they give you temperature, pressure, right? They're asking for volume. You're going to have to use PV equals nRT. That's my, I guess, take-home message here. When you see all these things in the word problem, they start, okay, here they're asking for volume, but there's only one way to get volume, and that's PV equals nRT. But they give you temperature, they give you pressure, and all this stuff. You're going to have to use PV equals nRT. What volume of CO2? Okay. So we know P. We're going to solve for this one. Right? We know R. And do we know T? Yeah. All we're missing is little n. All we're missing is little n. So how would we get it? Do we convert the 327 grams of lithium hydroxide into moles and use that for little n? Right? This has to be moles of something. It has to be moles of CO2. The gas, the only gas that's there. Right? Mole bridge. Someone said it. Someone sees it. Right? So we'll get the moles of LiOH. Get the moles of LiOH. Right? Use the mole bridge. How do you spell bridge? Bridge. To get the moles of CO2 to get CO2 moles. And then what do you do with the CO2 moles? What are you going to do with it? Put it in as little n. Put it in here. And solve for V. Janet, you see the game plan? Did I lose you? Where did I lose you? So the little n has to be moles. So the only way for us to get volume is to use PV equals nRT in the first place. We have to use this. And then I think the reason why in my head I have to think of little n as the moles of CO2 is because little n can't be moles of a liquid, can't be moles of a solid. It can only be moles of a gas. Because that's the only thing that can make pressure. That's the only thing that can, you know, it's going to fill up the whole container, right? So little n has to be moles of gas in PV equals nRT. So I guess that's the other trick to this, is realizing that little n has to be moles of a gas. Because that's the only thing that'll give you pressure and a volume to fill up a container, right? A gaseous volume. Because that's a gaseous pressure, a gaseous volume, right? Okay. We'll come back and work some of these. I just want to see if we can set them up. Here we go. Let's work through this whole one. If we can work through this whole one, I think we're really, that'll be a big help in getting you through your homework here. So let's completely solve this one. Now, Christina, when they say they're giving you this big table, right? Or they just use the words collecting over water. You think, oh man, this is one of those problems that I have to do what? The pressure is going to be here's a hint. The pressure is going to be that they give you. The pressure is going to be too high, all right? Because it's not only the gas that they collected, but it's also water. So realize when they collect a gas, collecting a gas over water problem, you have to look up the water vapor pressure, and you're going to be subtracting it at some point in the question, right? That's just what I'm trying to get at. Okay. When they say collecting gas over water, the pressure is going to be too high, so you have to correct it yourself. You have to subtract out the pressure due to water. Okay, so let's go ahead and solve this. 3.85 liters of CO is collected over water. 25 degrees Celsius, 689 millimeters of mercury. How many grams of HCHO2 were consumed? So Janet, what would you do first? I'm trying to figure this out. Yeah, good. Which one? Which one should we mess with? PV equals nRT? Bianca says PV equals nRT. Yeah, that's the one I would shoot for too. PV equals nRT. Notice how, if you go back in all these equations you have to pick from, right, a lot of them you can rule out. There's no talk about partial pressures. There's no talk about, oh, the total moles, right? There's no talk about a lot of this stuff. You're really just left with one. And then you can be messing with subscripts on it if you want, but really you only have one choice. Okay. Good. Janice got us started. Ashlyn, what would you do now? Good. Take away the water pressure from the total pressure. So really, if you want an equation, that's this one. But I think it's more complicated to look at the equation. I like what Ashlyn said. She said, man, just take away the water pressure from the total pressure, right? So here's our total pressure, 689 millimeters of mercury. Take away the water pressure. Which number should I be subtracting? Jessica, which number should I be subtracting? Can you read it? We are at, we're at 25. Yeah, that's what I see too, right? Subtracting the 23.8. Notice how we like to have pressure in atmospheres? Don't do that yet. Because you'll convert this guy to atmospheres, and you subtract out millimeters of mercury, then the whole thing's messed up. So don't do converting yet, right? Don't jump ahead. So we subtract that out. If you wanted to use the equation, this dude's 689, right? And maybe just erase the A and the B and write CO and H2O or something, right? And this guy is the 23.8. But I don't think you need to. I can just do what Ashlyn said. She said subtract out the pressure due to water. So we do that. 689 minus 23.8. About 665.2. And that is the pressure due solely to CO. Okay. Now what? A duffel. Now what? What would you do now? Yeah, we needed an ATM so we can prep it to plug into our equation there. 665.2 millimeters of mercury times 760. That's to go on the bottom. Millimeters of mercury in an atmosphere. So divide that by 760, about 0.876. Okay. Now what? Gloriana, now what?
Just plug everything
Into where?
in, the equation.
PV equals nRT. Yeah. All right. So our P, well, you can show it. PV equals nRT. My P has to be 0.876 atmospheres. My V, they said, is 3.85 liters. Nice, right? Don't have to do any converting there. N, R is 0.0821 liters, atmospheres, over moles, Kelvin. I like writing in all those units for R because then it reminds me what everything's supposed to be in and kind of one less chance to screw up. For example, the T, then you wouldn't write 25 degrees Celsius, 298 Kelvin. All right, you get your little N. Okay. So probably take the 0.876 times the 3.85, divide it by 0.0821, divide it by 298, about 0.14, 0.138 or so moles. Okay. So now we got our little N. Yesenia, now what? Convert it to grams. Is that what they wanted? I've totally forgot. Oh, you're right. Convert it to grams. But this is moles of what?
CO2.
That's moles of CO2. So if we converted that to grams, right, it's the wrong moles to convert to grams. Mole bridge first, then convert to grams. Right. So we'll have 0.14 moles of CO2. Okay, what is it? Oh, not CO2, it's just CO. And what is it? It's it's just 1 to 1. So that's not bad. 1 mole of this, what is it? HCHO2 for every 1 mole of CO. Now we can go to grams. And a mole of HCHO2. Let's see, H is 1, plus 12 is 13, another one is 14, and 32 should be like 46. Oh, thank you. I can't do jack in my head. 46. Okay. Now we should be there. 0.14 times 46. About 6.3 or so. That's what I got. Okay. So now you see that life has gotten a little more complicated, right? So realize in these questions, they start giving you volume, pressure. They could ask for a lot of different things. You know you're going to be using PV equals nRT, okay? And if you're not collecting over water, you don't correct the pressure, right? Like look at this next one. They're not collecting over water. There's no words at all about collecting over water. So then we do everything we just did, except don't correct the pressure, right? Don't do this. Don't do that. Otherwise, it's the exact same problem, all right? Use PV equals nRT to get the moles of the gas. Use this to get the moles of the gas. Use the mole bridge, and then convert it into grams. Okay. So come by and try it. Come by, and I'll be glad to help you out.